Welcome back. So we have covered all the combinations for a basic SR latch except for one, and that combination is when both the inputs S is equal to 1 and R is equal to 1. So let's see what happens now for this particular combination. So something like this: S here is 1, then reset is also equal to 1. Now, both the NOR gates, the blue one and the red one, have one of the inputs as 1. And the behavior of the NOR gate is that when one of the inputs is 1, the output will always be 0. Right? So this means that both the NOR gates instantaneously will have output as 0, owing to this one and this one. So that is the convention we have been using. So Q will be equivalent to 0, and simultaneously Q bar will also be equivalent to 0. Fine. Now this is a problem because as of now the two combinations, yeah, even the three combinations that we have been considering, the outputs Q and Q bar have been complementary, and that is what is expected. I mean, that is the stable behavior of a basic SR latch. But with this input combination, both Q and Q bar are having the same value, 0 and 0. Not only that, if we actually go through the analysis, because of the feedback connection, this Q will ripple here and this Q bar will ripple here, which means after some time, the second input of the NOR gate will be 0 and the second input of this NOR gate will again be 0. Fine. So S is equal to 1, R is equal to 1. Simultaneously, Q bar will change to 0, Q will change to 0. Fine. Which will then ripple back as per the feedback connection, which means the second input of both the NOR gates will change to 0. Now, the previous conditions that we have been considering, we started with the reset condition where S is equal to 0, R is equal to 1. It set up a state. Then immediately we change it to S is equal to 0, R is equal to 0 to maintain that state. Then we change S is equal to 1, R is equal to 0 to set up the set state. Then we immediately change it to S is equal to 0, R is equal to 0 to maintain the set state. So if I follow the same kind of analysis here, now that S is equal to 1 and R is equal to 1, and this thing has happened. So immediately after this, if I change S is equal to 0 and R is equal to 0, given that from the previous state, the second input of both the NOR gates is 0. So when I change S is equal to 0, R is equal to 0, both the inputs of these NOR gates are 0, which means now Q bar will be 1 and Q will be 1. So after this, I change S is equal to 0, R is equal to 0. And by making this change, Q bar changes to 1, Q changes to 1. Fine. So owing to these two inputs, this changes to 1, this changes to 1. And again, because of the feedback condition, this will ripple back here, this will ripple back here. And now this will change to 1, 1, which means after this condition is done, let me show it here, this will be 1, this will be 1. Fine. And if I continue with S is equal to 0, R is equal to 0, you know that 0 nor 1 is equal to 0. And again, this is equal to 0. So if I show it here, Q bar is equal to 1, Q is equal to 1, then after some time, because of the feedback condition, even if I keep S is equal to 0, R is equal to 0, it will automatically change to 0 and this. Then these will be again rippled back. Fine. Q bar is equal to 0, Q is equal to 0, which means after some time it will again change to 1 and 1. So we have a kind of oscillatory behavior. There are oscillations, and if I show it using a timing diagram, it is something like this. We have S is equivalent to 1, like this. Then I keep it 0. And if I show it for R, again R is equivalent to 1, then I keep it 0. So this is for R, this is for S. And the behavior is that Q will instantaneously change to 0. So Q will instantaneously change to 0, and so will Q bar. But after that, when I change S is equivalent to 0, R is equivalent to 0, it will start oscillating. And that is a problem. Oscillations are always bad. Oscillations in a digital circuit are extremely bad. So it will be something like this. It will oscillate between 1 and 0. And oscillations, it's not a stable state. You can actually, if you're savvy enough, you can actually, at least imagine what can be the repercussions of this. He's rippling, right? And same thing with the Q bar, right? So this one right here is Q, and this is Q bar. So this particular state is the problematic state, and we call this the indefinite state. It's an unstable state because when we put S is equal to 1, R is equal to 1, both the outputs of the NOR gate will be high. And eventually when we put S is equal to 0, R is equal to 0, the output breaks into oscillations. It keeps recursively, it keeps periodically going between 0 and 1, and that is not a stable operation. Right? So to sum up the behavior of an SR latch, basic SR latch, this is what we have done so far. We started with S is equivalent to 0, R is equivalent to 1. That set up my reset state. Then I switched to 0, 0 to maintain that reset state. Then we move to S is equivalent to 1, R is equivalent to 0 to set up my set state. Then we again switch to 0, 0 to maintain that set state. But as soon as we move to 1 and 1, it gave me what's known as indeterminate or an undefined state. Fine. And the problem is that immediately after this, when I go to 0, both of my outputs break into oscillations, and oscillations are never stable. Fine. So we had made that truth table. So the complete truth table for an SR latch will be something like this. We'll have S, we'll have R, then Q, then Q bar. So 0, 1, Q was 0, Q bar was 1, complementary state, a stable state. This is what initialized the reset state. Then 0, 0, again Q was 0, Q bar was 1, again a reset state, maintaining the reset state. Then I changed to 1, 0, Q became 1, Q bar became 0. This initialized my set state. And when I change it to 0, 0, it maintained this set state. But as soon as I go 1, 1, both the outputs go 0, which is not acceptable because they're supposed to be complementary of each other. We call this indeterminate or sometimes undefined state. Fine. And immediately after this, when I go to 0, I have what are oscillations, which means the output from the NOR gate continuously changes from 1 to 0, 1 to 0, and that is not a stable condition. This is a big problem with digital circuit. Right? So to sum it up, basic SR latch, it solves my problem in the sense that I'm able to store both 0 corresponding to reset state and 1 corresponding to set state But problem is that as soon as the condition 1 1 appears at the input, it goes into the undefined state, and immediately after the undefined state, my circuit breaks into oscillations. Right? So we can conclude that this basic SR latch, although it does give me the flexibility uh, that it can store both the bits, but problem is that basic SR latch is not practical because of this condition. Right? It's not a practical circuit. We can't use this in the design of a sequential circuit. Right? But it paves the way. It actually gives me the basic unit wherein I can store both 1 and 0. Now, what can be a solution to this problem? See, there can be two solutions. One, avoid this state. Avoid the state where S is equivalent to R is equivalent to 1. I mean, modify the circuit in such a way that this condition never appears in your circuit. This could be one of the solutions. Another solution could be define the state S is equivalent to R is equivalent to 1. Means modify this basic circuit in such a way that even if this combination appears at the input, it doesn't give you an indeterminate state, it gives you a well-defined state. Right? So the next lectures, we will be actually considering both the solutions. Starting with this, we'll come up with a circuit configuration where we will try to avoid this S is equal to 1, R is equal to 1. And then later on, we will come up with another circuit wherein we will try to define this state that even if it appears, my circuit should not break down into oscillations. Right? We'll be actually doing a series of circuits to store these bits. But the important thing is that this basic SR latch, it will be the core part always, because this is the basic circuit which stores your zeros and ones. The modifications, yeah, the new circuits that we'll be discussing, they will only try to avoid this condition and define this condition. S is equal to 1, R is equal to 1. But basic core unit that stores your bit is the basic SLI. So it's imperative that you understand the behavior completely fine. So we'll be doing the circuits in next lectures, but you will have one assignment here, and it will be the sixth question. Two questions I gave you in the physical class, three questions regarding to multiplexers as a part of online class. Now, sixth question will be discuss the behavior of an SR latch constructed using NAND gates. Fine. The one we discussed was based on the NOR gate. You can also construct a SR latch using a NAND gate. Fine. You know, in a NAND gate, if one of the inputs is 0, the output is always going to be 1. Fine. Just like in NOR gate, when one of the inputs is 1, output is going to 0. So work out the same combinations that we discussed for the NOR gate based SR latch for a NAND gate based. This will be an assignment. This will further clarify the doubts how these circuits work. Fine. So stop this video, and the next videos will be actually focusing on these two solutions, avoiding the state S is equal to 1, R is equal to 1, and later on defining the output for the state S is equal to 1, R is equal to 1, and that will give us new circuits which are more practical and which we can later on use when we design, when we come up with a methodology for the sequential circuits. So we'll stop here.